So we're almost there. Just bear with me because we're almost finished. Yes, I said finished with the penny lab experiment. I told you everything you ever needed to know about a penny is going to be in this lab, and we've analyzed a penny a multiple of different ways at this point. And now we're going to talk about one of the last ways that we're going to analyze the penny, and that is using a simple UV-Vis spectrometer. Keep in mind, in the last couple of modules, or parts of the module, you've learned that copper can make solutions turn color. So if we've got copper in a solution and we can get a colored solution, then why can't we analyze this guy on a UV-Vis spectrometer, right? Especially in the visible region, because visible meant color, and we could analyze colored solutions. And typically, the more concentrated the sample, the darker the color, right? And if we have a darker color, then the absorbance will increase. UV-Vis is going to tell me this information. And that's exactly what we're going to be doing in this part of the penny lab. So I'm going to switch over to the lab directions. And this is going to start the section that talks about visible spectroscopy. And it starts off by saying the dissolution of the pennies. Well, it gives you steps 1 through 6. Cut 2 pennies in half using a tin snip. Weigh 4 half pennies. Place them into the flask or the beaker. Add nitric acid to each. Make sure that everything gets dissolved. Add some water. Dilute it to the line with 100 ml volumetric flask. And then label them as P1, P2, P3, and P4. Well, if you're scratching your head and if you're reading the directions, you probably already wised up, because it says use initial AA penny solutions. So if you still have these around, and if you did not dump them, you are more than welcome to use those to start this portion of the lab. Because if I go back up to the AA, look what it says. Cut 2 pennies in half using the tin snips, weigh the half pennies, label them as P1, P2, P3, P4, add nitric acid, add water, dilute to the line to 100 mils. Well, from that point on the AA, we made some extra dilutions, but steps 1 through 5 basically put me right here. This is where I need to be. So if you've made these solutions and you have them around, feel free to use them. Do not weigh out more pennies. Do not dissolve more pennies. It's just extra work that you don't need to do. Next, preparation for spectroscopy. So once I have these solutions, and they are going to be colored because I've dissolved my copper and my zinc all up into some nitric acid, it says pipette 10 mils of each of the following into separate 50 ml beakers. The 1000, a 500 standard, a 250 standard, distilled water, and 10 mils of your P1, P2, P3, and P4. All right, so what we're doing here is that we are making a calibration curve. And here are the standards: a 1000 ppm, a 500 ppm, and a 250 ppm. Now, look at these. This is 0/00. That is an old school way of abbreviating part per million. Before ppm was used, we could also use 0/00, but this is in reference to part per million, but kind of a different concentration at the same time. Notice it says 1000 ppm, and it says a 0/00. A 500 ppm, otherwise known as a 0.5, 0/00. I want you to think about something for a minute. Think about percentage. When I think about percentage, this is based out of 100. We're always multiplying by 100 or dividing by 100 when we do 0/0. Well, 0/00 would maybe make you think that this is based on 1,000, and that's kind of where that old school term comes to. We don't really use this anymore, but it's in the lab for you to kind of look at and kind of tell you sometimes you might have those old school bosses and they're going to be using that type of information. But nowadays, we really focus on part per million, and we just rewrite that number a little different way. That's all that we do. So we're going to make a calibration curve. And with that calibration curve, we're going to, of course, turn to Excel, and we're going to graph that data. So we'll probably end up with a 3-point calibration. Now, depending on the year that you access this, we might tell you that 3 is not good enough. We might tell you to do around 4 to 5 different standards. So just make sure that you look at your paper when you print it off. Make sure that you're following the directions that it tells you to do. And this could include making more standards than 3. All right. The DI water is going to be the blank. So, of course, the blank, like we've mentioned before, especially in standards and solutions, should give me a 0 absorbance. And I can include that on my calibration curve if I want to. I mean, it should really be there because it is a sample that I am reading, and it has a signal, and that signal is 0. And then P1, P2, P3, P4, these are all coming from my samples from above. So I know that there's going to be copper present. I know that that should be about 2.5% copper, but I know that copper is going to be there. So if I'm running it and I'm not getting absorbance values for those, then I got a problem. I need to figure out what that problem is before I waste my time and someone else's time as well. So after I pipette 10 milliliters of each one of these into a beaker, and this is okay, we're keeping volumes consistent. That's all that we're after. We're keeping the volumes consistent. I'm going to then add 5 milliliters of ammonium hydroxide. This ammonium hydroxide, that 3 should not be there. All right, so I'm just going to mark that out. NH4OH into each of the 8 solutions. If the precipitate does not dissolve, add 1 ml additions until it does dissolve. The problem here is that this has got to be consistent though, right? I can't just pick one of these and add a ml of extra volume to it and not do it to all the others as well. That doesn't make any sense, right? I've got to keep things consistent. I have to make sure that everything across the board, everything stays consistent in the volume. So if I add 1 ml of the ammonium hydroxide extra, then I'm going to have to add it to all of these as well to bring everything on scale. I can't just do one and pretend like those numbers are going to work out. All right, so after I do that, I'm going to get a colored solution. I'm not going to ruin it for you, but these will be colored. That is why I'm going to be running them on a vis, which means that a plastic cuvette is going to be okay with this analysis. This is liquid solutions. They are in the visible range, and in addition to that, they are in the visible portion with DI water as a solvent. So plastic is going to be perfect. It's going to tell me store the baseline with DI and the ammonium, right? I've got to add the ammonium to that as well. Hopefully that doesn't turn color. Hopefully that will just be clear and colorless. But that ammonium hydroxide with the DI water should be baseline between the range of 550 to 650. This at 50 nanometer per minute, this just gives me the speed. And this is an old setting that used to be done on our older UV-Vises. But our newer thermogenesis models, they don't really ask. They just kind of say fast, slow, or medium, or something silly like that. So just use the default setting that you're seeing up on the software screen when you start it up, and you'll be okay. But 550 to 650 is going to be the window. Number 2, it says scan the 1000 ppm solution to obtain the maximum wavelength. So what will happen is that on the UV, I will probably see at least one hump, and it will come back down and maybe go back to baseline. My lambda max, again, is the peak at the very top. So the highest peak, not the highest wavelength. So if I'm seeing little bumps and stuff out here that might show up, those are not the maximum wavelengths just because they're higher numbers. The maximum wavelength is the highest height that I'm getting from a peak. So whatever the lambda max is, that is going to be my go-to, or on the thermo units, my fixed position. So I'm going to run everything at the best wavelength that's possible. So I choose the 1000 ppm because it is the strongest, and I'll typically get a better curve because of that. I mean, there's quite a bit there. It's going to be very easy for the machine to determine the strength or the concentration of that all the way through the wavelengths, and I will get a very smooth, very dominant curve because of it. So once I scan the highest standard, that will give me the fixed number. And let's say that my fixed number is 625. For some strange reason, let's say that that's what it is. Then I will switch the mode of the UV, and I will make it go to 625, and I will make it run everything at 625. But your lambda max is going to be based on your number, your 1000 ppm that you run. It might not be 625. It could be a completely different number, but it will be between 550 to 650 because that's where we're telling you to scan it. Number 3, go to the lambda max and read the absorbances for all of the 7 solutions. And then finally, number 4, determine the part per million copper and the percentage of copper based on the UV-Vis data. All right? Okay, so how do I do these calculations? What's the chemistry that goes on behind all of this? And what does the spreadsheet look like? That's always the questions that you'll have, right? And that's what we're getting ready to talk about. The issue here, though, is I'm not going to go through the chemistry. And the reason I'm not going to go through the chemistry on this is because the chemistry is the same as with the UV instrument. Okay? There is no difference with that. So if I scroll back up here to the top and I look at what we talked about in the previous video about adding nitric acid, all of this stuff, and then in the previous method from there, we did add things like hydroxide to it, ammonium hydroxide and sulfuric acid. So if you want to go through and take a review of all of the reactions that happened in those procedures, it applies to this as well. There is no difference here. We're using the same reagents. We're just using a different instrument in order to do the job. That is it. All right. So I'm not going to talk about the chemistry. That's already beating a dead horse, and we don't need to beat it anymore. So now what we want to do is maybe take a look at the spreadsheet and talk about what I should maybe include in this part of the lab. So I'm going to scroll down just a little bit, and what you're seeing on the screen is a calibration curve. All right. So up here at the top, it looks like here are my standards, or my 1, 2, 3 is how I labeled them, or how this person labeled them. And then here are the milliliters that was used, because they used a 1000 part per million solution to do this with, and they were required to make their own 1500 and 250 ppm. So this basically told me that they took 5 mils, they diluted it to 10, that gave them the 500, and then they took 6 1/4 mils, diluted it to 25, and that gave them a 250. However you want to do it, that's up to you. The object of the game, though, is to get a 1500 and 250. We don't really care how you do it, as long as you get to that point. In addition to that, you're probably thinking volumes. How much do I need to prepare? Well, notice this procedure said 10 mils of it at least. So you're going to have more than 10 mils. So either do 10 mils exactly, or do more than 10 mils and pipette the 10 mils out that you need to use. All right, and then we ran those. After we added the ammonium hydroxide and stuff, we got some absorbance values. There they are. As the concentration increased, the absorbances increased. And then here on the calibration curve, that is what that looks like. Now, ideally, you would want to put a 0, 0 in here, or whatever the blank gave you, whatever absorbance that is, that's the number that you would want to put there to give you a better linear regression line. This person didn't do it, though. All right, so here's the regression line, 0.0006x plus 0.0105. And then they analyzed the P1, P2, P3, and P4 samples. These are super strong, right? And that's okay. UV-Vis is not as sensitive as AA when it comes to metals. So there's going to be colored solutions. They have to be strong enough to be seen, because if you can see those colors, the UV-Vis can see the colors. And it doesn't really work at very low concentration values. Now, of course, too high can be a problem. But these are okay with little more concentrated samples to be analyzed. No big deal here at all. So P1 through P4, we added the ammonium hydroxide to those. We analyzed them. Here are the absorbance values. And then those absorbance values got plugged up into this equation. All right, so what this person did is that they put 0.257. Let me get rid of that. Switch it over to a pen. 0.257 equals 0.0006x plus 0.0105, and they solved for x. So they subtracted the 0.0105 from each side, and then they divided by 0.0006, and what they ended up with was 410. And they did that to each one of them. So 410, 387, 299, and 295. All right, so those are the parts per million according to the penny. So down here at the very bottom, you're going to see another line that this person has created. And what they've done is that they've taken the gram that penny half weighed. Now, if they use the part from AA, no big deal. They just keep using that gram because it's the same. If it's the same solution, no issues there. But if you had to cut new pennies, then you're going to use those new weights for those halves. And it looks like they diluted that penny down to 100 mils. I mean, that was kind of the very first step in that part of the procedure. So they were able to take this gram and they were able to change it to milligram. And then this is 100 milliliters. So they had to convert that over to a liter. And once they did that, they could divide these two numbers. So milligram over liter is my part per million. And that's how they got that part per million value. So if the penny was 100% copper, that's the issue here, 100% copper, then this would be the value that penny would kick back on the UV-Vis. But we know it's not. We know that weight is not entirely copper, that really only about 2.5% of that weight is going to be copper. All right, so on the UV, when I analyzed that part of the penny, it looks like it gave me a 410.8. So to calculate the percent of copper, I'm going to take the 410.8, which is the part per million I received from the instrument. I'm going to divide that by 12,407, because that's what the part per million would be if it was completely copper. And then I'm going to multiply that by a 100. And this should give me 3.3-ish as far as the percent of copper. Well, they did that with every one of them. So each one had its own weight, right? Each one was brought to the same volume, but each one had its own weight. We converted all of those over, did the same calculation all the way through, and it looks like my P3 and P4 are a little bit better numbers, 2.4 and 2.3, versus my P1 and P2 values, which are 3.3 and 3.1. So we took all four of those and we did an average. The average comes out to be 2.803. I also did a standard deviation of those four just to see how close the values are. And of course, they're not very close. That standard deviation should have been a little bit better. There's only so much I can do, though. And the reason is because the pennies, statistically speaking, are going to be different. However, if I'm factoring in those weights and those differences, then I should at least get a closer number than 3.3 one time and then 2.4 the other time. So the accepted value here again is 2.5. So I'll go through, and it looks like that I'll compare that 2.8 to the 2.5 and do a percent error calculation. Again, the percent error calculation, you take the difference, so the theory of what it should be minus the actual of what you've got, divide it by the theory of what it should be. So the difference divided by the accepted value. And this person got 12.1% error. So if you compare all of these